Okay, next up will be Tony Brake. He's a senior bridge engineer from CALTRANS with 18 years with CALTRANS. He's a supervisor of bridge maintenance and design in Los Angeles. And back in 91, 97, he worked in our bridge design office in Washington and a good friend of John Van Loon.
Thank you, Chris. My name is Tony Brake. The last name Brake is spelled with an R and not exactly an L. I am a senior bridge engineer with CALTRANS, California Department of Transportation. I am a supervisor of a design branch located in downtown Los Angeles in a high-rise building about 13 stories high right across from City Hall. CALTRANS has broken apart California into 12 districts, as you see on your left. The districts 1 and 2 are the northern part of the state, and the bottom part of the state, 11, 8, 12, and there is District 7, which is Ventura County and Los Angeles County. That's where I work with my office. CALTRANS, or I should say California, is broken into 58 counties. And based on this color coding, you can see the distribution of the bridges within California. So you can see, and the southern part of the state has quite a huge number of bridges. Now, to handle this design, there are basically 3.5 maintenance bridge design sections within CALTRANS. I supervise one of them in Los Angeles. There are 2 up north in Sacramento, and it's kind of like a half-sized one in Oakland. That's just for bridge maintenance design purposes. Overall in CALTRANS, with bridge design, there's somewhere around 22 different branches entirely. It's quite a lot of people. Statewide ages of bridges are shown here. The average age is about 43. State highway bridges number around 13,000. Local agency bridges another 13,000. So we have a total of 26,000 bridges in California. That number is horrendous. And the age of 43 average is very significant because when you hit, well, from what I've discovered, is that when you hit 40, everything starts kind of, the serviceability of the structure starts going down. The tipping point is around 40, and we're seeing some very, very significant problems, issues nowadays with quite a few of these bridges. This is how CALTRANS spends its money for a bridge of major maintenance. Decks, approach slabs, 51% of the money, joints, about 7%, paint projects, 24%, all others, 18%. The state highway maintenance program, we call it a 315 program. Last year we spent $146 million. And the State Highway Operation Protection Program was, last year we programmed $300 million in projects. That's quite a lot, that's massive. But the SHOP projects have matching federal funds. The 315 program is purely state funds. So needless to say, we do everything we can to program as much as we can in SHOP because we do have matching federal funds. But the SHOP projects also include bridge replacements and deck replacements, as well as deck rehabs and joints. I'm going to be talking about 9 conventional joint types within California, the common ones, and 2 seismic joint types that are used within California. I'm going to start off with a definition of what a conventional expansion joint is. It's usually a joint that accommodates longitudinal expansion and contraction movements or service demand conditions of bridge superstructures upwards of around 15 inches. They are not designed for seismic design or demand conditions. Those joints are expected to see significant damage in a massive earthquake. Seismic expansion joints, they can accommodate upwards of 50, possibly 60 inches of movement in an earthquake. The joint is expected to maintain its full functionality with 0 to minor damage after a significant earthquake. Okay, let's go to the conventional joint types. This is a type A and type L expansion joint. The type A is a silicon sill pourable, as you can see on your right. The type A is for transverse joints across the bridge. And the type AL is basically a silicon pour joint, which is for longitudinal purposes. What sort of issues do we have with these joints? Never-ending problems with joint spalls. As soon as those joint spalls start happening within the joints, the joint is basically made worthless. And as you can see on the picture to your right, you can see all those squares across the joint. Those are joint spalls that have been repaired, and you see in the bottom of the screen, suddenly it started to fail. And when we have failure of the joint spalls, the joints are no longer sealed, and we have a failure of the joint. Now, what we are finding is that when we repair these joint spalls, and of course replace the joint seals, within a matter of possibly a year and a half, all of the joint spalls, quite a few of it, is spalling off once again. It's a matter, we discovered, of materials, construction, and possibly specifications, but it's becoming a very costly issue in California. Now, the picture to your left, that blue shoe is my shoe, and that is my foot. I went out to take a look at a type A expansion joint. It has maybe 5 feet of completely debonded, and it's only like 1 year old. The rest of the joint is intact, it works, it's functional. In this case, I think this is a construction-related issue. The picture to your right is the consequences of what happens when you have a type B or a type A joint at a hinge sill. It fails, the joint fills with debris, and the diaphragms at the hinge basically crush themselves. So just replacing the joint sills for, say, maybe a few thousand, 20-some thousand bucks, you end up with a complete hinge reconstruction project for several $1 million. So it's very costly to keep these joints replaced and clean. And as a side note, I've noticed in the past 6 years, we're having a lot more complete hinge replacements in California than we have had in the past. This is a type B expansion joint sill, transverse. It's movement rating less than or equal to 2 inches. It's a preformed elastomeric joint. It's compressed, and then it's squeezed into the joint itself, as you can see on the picture to your right. Some of the issues we have with maintaining these type Bs. Once again, it's a never-ending joint spar issue. We have armored angles on either side of a joint. The studs that anchor the angles into the concrete fatigue, they break, and then these armored angles come flying off into the traffic. So this takes about 35, 40 years to happen. At this point in time, we do not go back and put armored angles in that joint. We completely rip that joint apart and reconstruct it, go with a drawn bond concrete, and possibly go with a type B joint sill. And then the picture to your left, there's that strip of concrete there that's all patched up. That's what we call a back wall. This is a part of the substructure that shoots up to the surface of the deck. What you have on your left there is a bridge that's a short seat abutment type. It's on elastomeric bearings. It's moving. And behind it, we have a back wall. And the back wall, after about 35, 40 years, it just totally starts to disintegrate. And we have major safety issues there. And so in that case, we just rip it apart, rebuild it, or put approach slabs there, which span over the back walls. What you have on the right is a type B construction, or type B joint that was replaced. We put new concrete expansion headers on either side, rapid street concrete, and within a short period of time, a few months, the entire concrete was falling into pieces on us, just brand new concrete. So I received a phone call from construction personnel asking me, hey, what should we do, Tony? My response was, go out there and rip it apart, rebuild it, redo the whole thing. Fortunately for us, the contractor was still on site. The contract had not been accepted, so the contractor was on the hook to get it done. But what's interesting is the same contractor rebuilt this joint, used the same materials, the same joint type, and the second time around, it came out perfect. Okay, some other issues with type Bs. We have age-crushing bulging. Picture to your left, the upper part of it is just a completely crushed joint. The picture in the middle, you see it's no longer compressed. It has a strip that's open. The joint has failed. The joint on the right, once again, never, ever ending joint spalls, destroying the joint. And we actually have some bulging in there. In this particular design, we are going to completely rip out that joint, rebuild it with a drawn bond rebar and concrete, and probably put a type B joint sill back. Okay, the third type is a asphaltic plug expansion joint sill. It basically has a bridging plate with a location or a pin beneath it to hold it into place, and then we have asphaltic joint material on top. You can see on the picture on the right, it's being put into place on a bridge, and it happens very quickly, and it's very easy to do. Some of the problems we have with these joint types: the bridging plate comes loose, it breaks, it starts bouncing around, it starts punching holes into the upper joint material. The picture on the right, we have a so-called flexible asphaltic plug that's been out there for far too long. And it's aged, it's cracking, it's falling to pieces, and you can see, you can just dig right into the the AC on both sides, as well as the middle part of it. This is a fourth type of common joint type. It's a common for Southern California, starting in about the year 2006. The picture to your right is the first one we installed down south in the year 2006, but I shot a picture of 2007. The pictures to your left are the common bonded joint seals. We call it bonded because we bond the sides with epoxy. The picture to your left is manufactured by Watson Bowman. It's actually bonded on both sides with epoxy, then it's actually inflated with air to help to force the joint and the epoxy into the concrete headers. Now, the problems we've had so far since 2006 has only been one problem with one joint. And it happened where a partial length of that joint had failed. It was able to cut it out, put a new splice in there, and epoxy it back into place. The bonded joint seals are excellent for joints with skews over 20 degrees, and that's because of shear. And we continue to use them, and I'm very, very happy with them. The fifth type of common seal type is a strip seal expansion. You can see on the left, we have armored angles with studs holding it into place with concrete headers, and then we have a neoprene gland running down the center. Some of the problems we have with this joint type is the neoprene gland, of course, will eventually tear. The material, something else, bulges it down and it tears. That's the most common type of problem we have. Sometimes the armored angles, the studs will fatigue and break, and the armored angles will come loose. We have to replace that portion. The problem with strip seals, from what I've seen, is that each one is proprietary. We have like 4 different manufacturers. They all have different neoprene glands for their particular joint type. So we have to go out and sole source it just to the company that manufactured the joint to start with. And sometimes we don't have shop plans in our as-belts showing us who manufactured the joint to start with, so it can be very difficult, sometimes almost like searching for a needle in a haystack to try to find, the neoprene gland that's to be used to replace this. The sixth type of common joint seal is a modular expansion joint seal, as you see. You see from the left, there are a lot of components involved. You have transverse beams on top, and underneath it, you have longitudinal beams that expand and contract. The picture to the right is one in Southern California. It's very large, relative to most of the ones I see in Southern California. This is the problems we have with these joints. The welds start cracking, and they fail, and the transverse beams just come flying off, or else we have a failure of bearing in the longitudinal beams underneath the transverse beams. Once it's failed, then the top transverse beams just start flopping around, and before you know it, they break, and basically they come flying off into traffic. And the picture you see at the right is a typical failure of, say, a weld in these transverse beams. Typical, or I should say some of the failure modes we have with the modular joints: spall and failure of the concrete headers, fatigue of welded connections, shop and field splice of the center beams. We have control spring failure. That's one of the components beneath the joint. We do have poor workmanship in construction. We do have excess concrete dumped into the joint opening. When we build the joint, we put expanded polystyrene in the joint, and sometimes it's not there. And when they pour the concrete header on the sides, they just dump concrete right into the joint, and lo and behold, the joint is frozen up and locked. We have a poor joint connection to the main deck reinforcement. The joint can be placed too high or too low. We have an incorrect joint seal alignment, and sometimes there is a design error. We select the wrong joint type for the application. Now this is a very interesting type of joint seal that I wanted to bring to your attention. This is an internal box girder flume. If you take a look at the picture to your left, this is a cross-section of a cast-in-place box structure. One of the cells serves as a storm drain channel. There's no piping in there, it just flows with water, storm water. And the joints at the abutments are what you see at the right. Now these have been in place maybe about 20 years, and now we're seeing failure after failure after failure of these type of joints. Picture to your right is a typical failure that you see from the exterior. Basically, the water is just pouring down the abutments. And to go inside, you have an option of sending an inspector in there in confined space. And the picture of the bridge to the right, within that box, it had bats flying around, and it had cockroaches crawling around about 2 inches long. So needless to say, nobody wants to go in there to perform a bridge inspection on those joints. So we have an option. To picture to the left, we can send in a robotic camera, and it does a great job. This particular one, it's like 119 feet. You can see from the right side bottom, it's already 119 feet into the box girder, and the results from this robotic camera are just excellent. This is the ACE type. It's a sliding steel plate joint seal. We don't use these anymore for new bridges. But they are still out there in the inventory. This is some of the problems we have. As I've mentioned before, the armored angles, the studs snap, and then the angles come flying off into the traffic. So when this happens, we don't even bother to try to repair that. We just rip it out and draw on bond, concrete, put a type B or maybe a type A, and just replace the whole thing. And sometimes that movable gap in the top of the steel plate, it just gets filled with the debris of every kind, so the bridge joint is not serving contraction and expansion anymore. And sometimes it just gets, that is paved over with AC, and the gap is just filled in with AC, so it doesn't function any longer. Okay, type 9 is a steel finger joint for very large movements. We have a few of those down in Southern California. Some of the issues we have with the fingers will break. They come flying off. Those bolts will break as well under live load fatigue, and then the fingers come flying off because of broken bolts, or maybe entire sections. If you can take a look at this joint here comes in sections. Those bolts holding it down, sometimes they snap, and the whole section of the finger joint just comes flying off into traffic. And then the joint type to the right is from the Vincent Thomas Bridge, Long Beach, went in 1963. I don't know what they're thinking at the time, but now, I mean, that's a deadly hazard to bicyclists. And now we're in the process of trying to do an upgrade or repair on that. At the time, I guess 1963 bicycles weren't considered important or part of the traveling roadway. Okay. Off of conventional joints, let's go to seismic joints. This is a MAURER swivel expansion joint. The picture to your left is actually taken in Seattle. It is a relatively mural bridge. You can see this is a monster-sized modular joint. And from the diagram to the right, it's got a lot of moving parts and a lot of components. From my practical experience, and I don't mean to slander any company, is that the more moving parts you have out there under live load, the more maintenance problems you can expect to have. We currently have 3 bridges in California that have this joint type. The new Carquinez Suspension Bridge in the northern part of San Francisco Bay Area, it's got a total of 50-inch movement for seismic. San Francisco Oakland Bay Bridge, brand new one, the Skyway, and then Hillary Drive Overcrossing in San Diego County. Some of the problems we've started experiencing already with the new Carquinez Bridge, built 2003, we have at Pier 1, abutment 4, problems found in year 2012, put into place in 2003. You can see from pictures to the right, it looks like the neoprene stirrup bearing moved to the right, the bearing was lost, cracking. So a contract was issued back in 2015 to keep the joint, but just repair it. Okay, the last joint type I'm going to talk about is special in-house to California. This is basically a bolted steel plate on top of a deck. It can have a surface movement from 4 inches up to 13 inches, seismic movement upwards of 50 to 60 inches. It's quite huge. The steel plate on top is anywhere between 3 to 5 inches thick. And from the left side, it is bolted into a special box embedded into the bridge deck. From past experiences, whenever we bolt a steel plate into a deck, put it under a lot of traffic, the bolts break and the steel plate comes flying off into traffic. In this case, we hope to mitigate that by putting alternated elastomeric washers with steel washers onto high-strength bolts, as you see from the left. The standard drawings became available in 2014 with CALTRANS, so it's relatively new. These are some pictures of what we have out there right now on several bridges. I may go back one. The top wearing surface is a multiple layer polymer. And we know over time, with wheels of traffic, it's going to wear it. So we know we're just going to grind off where those wheel strips are and just put it back. So we know how to mitigate that issue. And I know that's going to become a maintenance problem that we have to deal with in the future, but we can't successfully mitigate it. Okay, my second to last slide, some of our general maintenance concerns. Now, I don't mean to slander any contractors here, but generally speaking, the low bid, the contract goes to the low bidder. And the low bidder, he's undermining everybody to get the bid, and he plans on making his money back. And he does that by sometimes cutting short corners and sometimes coming back at us with CCLs. Not all of them do that, but we do have issues there. Time permitted for lane closure. To do the work in these heavy urban areas of Southern California, we only have lane closures or traffic windows of 6 to 8 hours. So that it's all done at nighttime, which means limited visibility, and it means that contractor, the person doing the job may be on his second job. He's got one in the daytime, now he's got one at nighttime, and he's tired, and he may not be doing his best. And then because we are in tight windows, we have to use rapid strength concrete almost everywhere. The construction inspection. Caltrans personnel in-house are not quality control personnel. They are quality assurance personnel. The contractor is supposed to provide quality control. Sometimes they do, sometimes they don't. Quality assurance means that sometimes the Caltrans inspector simply isn't there on site. And on top of that, we have a low bid contractor wanting to cut corners, and it can be a real mess. The materials, rapid strength concrete, sometimes it works, sometimes it doesn't, depends upon our specifications, the materials used, and the contractor's knowledge of how to use it. The age of the infrastructure, we're talking about an average age of bridges of 43. The tipping point I've discovered is around 40. So if you take a look at a type A joint cell, replace it every 10 years, it should have been replaced about 4 times now. Type B can last 20 years, so it should have been replaced maybe around about twice now. And we start seeing significant problems with decks as well as at the year 40, anywhere past that point. No warranty. Once the contract is accepted, that's it. The contractor walks off the site and we just bought it. No warranty whatsoever. Suppose he puts in a joint seal with a lot of spall repairs, and then 2 months after he leaves the site, all the spalls start coming off. Well, we just bought it. We can't do anything about it. We got to go in there and redo everything again. Now, work recommendations, trust but verify. Everything that goes into our maintenance contract is based upon the bridge inspection report that's performed every 2 years. I've made a policy of my design branch that when we accept a contract, my personnel and myself quite often go out there and we verify all the work recommendations. Because sometimes we go out there and the bridge has already been replaced, Sometimes the work has already been done by another party, so we don't want to put that into the contract. Sometimes the joints aren't as bad as what the bridge inspector thinks, and we really don't need to replace it. And sometimes the bridge has deteriorated so fast, so quickly, in 2 years, we get out there, we can't slip it into a maintenance contract. So we've got to pull the plug right then and there and declare an emergency and get the work done by an emergency contract. Okay, thank you.